in school staring at a tough multiple choice test. You don't know the answer, but you circle something anyway, hoping for the best. That's exactly how large language models behave when they hallucinate. This new study shows that hallucinations are not some mysterious glitch, but a simple statistical outcome of how models are trained. Even with perfect data, cross-entropy training makes them guess, just like test takers under pressure. And the problem doesn't stop there. Our benchmarks, the very tests we use to grade these models, often punish them for saying, "I don't know." So instead of staying cautious, they learn to bluff. The key takeaway is that hallucinations are baked into the system, a natural side effect of the incentives we set during training and evaluation.
All right, let's dive into this paper. It kicks off by framing the problem of hallucination with a really helpful analogy. Think of language models as students taking a tough exam. When they don't know the answer, what do? They guess. Why? Because our current systems reward a plausible-sounding guess more than an honest, "I don't know." The authors argue that this isn't some mysterious, emergent behavior. It's a direct result of how we train and test these models. They say it all starts with simple classification errors. During pre-training, the model is fed a ton of data from the web, and it can't always tell the difference between a solid fact and a well-written piece of fiction. If it can't distinguish them statistically, it's going to learn to produce both. So why does this problem stick around? Well, that's the second part of their argument. Our benchmarks and leaderboards are basically exams with no penalty for wrong answers. Guessing becomes the best strategy to maximize your score. This means we're optimizing models to be good test takers, not necessarily truthful communicators. To make this concrete, they give a simple example right at the start. They asked a powerful model for an author's birthday, but with a key instruction. If you know, just respond. The model didn't know, but it confidently gave 3 different wrong answers anyway. This shows the model isn't just getting a fact wrong, it's completely ignoring the user's explicit instruction about uncertainty. And that's the core problem they want to solve. Now let's get into the root cause of these hallucinations, starting with pre-training. Take a look at Table 1, it's a great example. The authors asked 3 major language models for the title of one author's PhD thesis. All 3 gave different, confident, and completely wrong answers. This isn't just a simple mistake. It's a creative fabrication, which is exactly what they mean by hallucination. From here, the authors make a pretty big claim. They say that even if the training data were perfectly clean and error-free, the very process of training a language model would times lead to it generating errors. You'd think perfect data would lead to a perfect model, but they argue that's not the case. So how do they explain this? They reframe the problems. Instead of thinking about language generation, they simplify it to a binary classification task. Imagine for every possible sentence, the model has to decide, is this a valid, true statement? They call this the "is it valid" problem. By looking at it this way, they can bring in tools from classic computational learning theory. The idea is that a language model, by learning to predict the next word, is implicitly learning a classifier to distinguish good sentences from bad ones. And as we know from machine learning, no classifier is perfect, especially when you're dealing with the massive complexity of real-world language. This sets the stage for a more formal, statistical explanation of why errors aren't just possible, but inevitable. Okay, this is where we get to the heart of the technical argument, and they use a really clever visual to explain it. Look at Figure 1. The authors are showing why models make mistakes, and they break it down into 3 types of problems. First, you have simple cases like spelling. A good model can easily learn the rule that greetings is correct, and gradings is not. If you look at the diagram, you can see a clean line separating the good examples from the bad ones. Simple enough. Second, they consider a harder problem, like counting letters in a word. Here, the underlying pattern might be more complex. The diagram visualizes this as a straight line trying to separate a circular pattern of data. It's just not going to work. This is what they call a poor model for the job, so it's guaranteed to make mistakes. This is all about model capabilities. Third, and this is the most important one for hallucinations, they look at arbitrary facts, like birthdays. There's no real pattern to learn here, it's just random data. The diagram shows the good and bad examples all mixed up. No matter where you draw the line, you're going to be wrong a lot of the time. The only way to get these right is to memorize them, and if a fact isn't in the training data, the model has no choice but to guess. Then, they introduce a simple but powerful formula. It says that the rate at which a model generates errors is at least double the rate at which it messes up this "is it valid" classification. This directly connects the abstract idea of classification to the concrete problem of hallucination. If a model is even a little bit confused about what's true or false, it's going to generate a lot more errors. This brings us to the central argument about why hallucinations persist even after training. It's all about the tests we use. The authors bring back that student analogy. Language models are evaluated with a scoring system that gives 1 point for a correct answer and 0 for a wrong one or a blank. In a system like that, what's the best strategy? Always guess. This creates a huge misalignment. Humans learn from the school of hard knocks that being confidently wrong can have real consequences. But language models exist only in test-taking mode, where there's no penalty for bluffing. So they're optimized to produce specific, confident-sounding answers like September 30th, instead of safer, more honest ones like sometime in autumn. The authors then make a bold claim. They say that simply creating new, specialized tests for hallucination isn't going to fix this. The real problem is the epidemic of existing benchmarks that dominate the leaderboards and implicitly reward this guessing behavior. Think about it. Imagine two models. Model A is honest and says, "I don't know," when it's unsure. Model B is a gambler and always guesses. On our current tests, Model B will almost always get a higher score, even though Model A is far more trustworthy. The solution, they argue, isn't to add another small test. It's to fix the scoring on the big, important tests that everyone is already using. So after laying out the high-level problem, the paper dives into the technical weeds of pre-training. But first, it touches on some related work. It highlights a crucial trade-off. You can't have it all. A model that tries to be creative and cover many topics will inevitably hallucinate. If you force it to be perfectly factual, it might become repetitive and boring, a phenomenon known as mode collapse. It also mentions popular techniques like reinforcement learning from human feedback, or RLHF, which are used to clean up models after pre-training. While these methods help, they aren't a magic bullet and, as we'll see later, can sometimes even make things worse. Then we get to the main event, Section 3, Pre-training Errors. The authors frame pre-training as a classic machine learning problem called density estimation. This just means the model is trying to learn the underlying probability distribution of language. Basically, getting a statistical feel for what makes a sentence plausible. They use simple notation for this. P is the true, perfect distribution of language, and P hat is the model's best attempt to learn it. The goal is to make P hat as close to P as possible. They also cleverly address a potential counter-argument. What about a model that only ever says, "I don't know"? It never makes an error, right? But, as they point out, such a model is useless because it hasn't actually learned anything about language. It fails the basic goal of density estimation. Alright, now we're getting into the mathematical core of the argument. The authors start by making an important clarification. This isn't just about autocomplete. While models are trained to predict the next word, their analysis is deeper. They're looking at the model's overall understanding of language statistics, not just its ability to complete a sentence. Then, they formalize their big idea. First, they define the model's generative error rate. This is super simple. It's just the probability that the model will produce a sentence that's considered an error. Think of it as the model's raw mistake frequency. Next, they set up that "is it valid" classification problem they've been talking about. They create a hypothetical data set. Half of it is made of real, valid sentences from the training data. The other half is made of uniformly random error sentences. The classifier's job is to tell them apart. Finally, they show how to build this classifier directly from the language model itself. The rule is simple. If the language model assigns a high probability to a sentence, the classifier labels it as valid. If the probability is low, it's labeled as an error. The "is it valid" misclassification rate is just how often this classifier gets the label wrong. This setup is the bridge that connects the model's ability to generate good text with its ability to distinguish good text from bad. And here we have the theoretical punchline. The paper presents a key formula, Corollary 1, that connects all the pieces we've just discussed. In simple terms, the formula provides a guaranteed minimum error rate for any language model. It says the model's tendency to generate errors is directly tied to its ability to distinguish facts from fiction. The authors use the birthday example to make this crystal clear. For any given person, there's one correct birthday, but 364 incorrect ones. The number of errors is huge compared to the number of valid answers. Their formula shows that because of this imbalance, even a model that is trying its best will inevitably make mistakes on these kinds of unlearnable facts. Just a mathematical guarantee of hallucination for certain types of knowledge. Next, they tackle a subtle but important detail, the miscalibration term, which they call delta. This term basically measures how well the model's confidence aligns with reality. They argue that for any well-trained model, this delta value has to be very small. Why? Because of how models are trained. They use the standard cross-entropy loss function, which punishes a model for being surprised by real data. The authors show that if a model were poorly calibrated, meaning delta was large, you could easily tweak its probabilities to get a better score on the training objective. Since the training process has already found the best possible model, this can't be the case. Therefore, the model must be well calibrated, and delta must be small. This page provides the visual proof for those claims about calibration, and it's a real eye-opener. Take a look at Figure 2. It shows two charts comparing a model's confidence to its actual accuracy. The goal is for the blue bars to sit right on that dashed line, which represents perfect calibration. The chart on the left is the base model, fresh from pre-training, and look at that, it's beautifully calibrated. When it says it's 80% confident, it's right about 80% of the time. Its self-assessment is honest. Now look at the chart on the right. This is the same model after it's been fine-tuned with RLHF to be more helpful. The calibration is a mess. The model is now wildly overconfident. When it's 90% sure, its actual accuracy is closer to 60%. The very process we use to make models better is also making them less reliable judges of their own knowledge. This is the core of their argument. They state that hallucinations are inevitable, timed specifically for these well-calibrated base models. Their math shows that a model trained to be perfectly calibrated times must make errors on unlearnable facts. If it didn't, it would have to be miscalibrated, which contradicts how it was trained. So the errors we see aren't just a bug, they are a natural consequence of the training objective. This sets up the next step, extending this whole framework to handle prompts, making the analysis even more relevant to how we actually use these models. Okay, so now the analysis levels up by officially bringing prompts into the picture. Everything we've talked about so far is now generalized to the way we actually use these models. We give them a prompt, and they give us a response. The authors present Theorem 1, which is the souped-up version of their main formula, but the core message is exactly the same. The rate at which a model generates errors is guaranteed to be above a certain threshold. This threshold is still determined by how bad the model is at telling facts from fiction, multiplied by a ratio of how many valid answers there are versus wrong ones. The new formula is just more robust to handle the complexity that prompts add. With this powerful tool in hand, the paper shifts gears. It says, okay, we know that times errors happen, now let's diagnose the asterisk why. They're going to break down the different reasons a model might fail at that is it valid classification task. They start with the big one, arbitrary fact hallucinations. This is for stuff like birthdays, where there's no clever pattern to learn. You either know it or you don't. They connect this to a classic machine learning concept called VC dimension. High VC dimension just means a problem is really complex and requires a ton of memorization. To study this, they create a formal definition of an arbitrary facts game. It's a simple setup. For any question, there's a pool of possible answers, one of which is correct. The ground truth system either gives the right answer or says, I don't know. This perfectly models the challenge of learning a large, sparse set of facts. This page gets right to the point about why models struggle with facts. It's all about rarity. Models have no problem with Einstein's birthday because it's all over the training data. The real issue is the huge number of facts that appear only once. To formalize this, the authors introduce a simple but powerful metric, the singleton rate. This is just the fraction of training examples that are unique, one-off facts. They explain that this rate is a great way to measure how much sparse, hard-to-memorize knowledge is in the dataset. Then comes Theorem 2, which is the big payoff. It presents a mathematical formula that directly links the singleton rate to the model's hallucination rate. The takeaway is incredibly clear. The more singletons you have, the more your model will hallucinate. It's a direct relationship. The theorem provides both a lower and an upper bound, which means this isn't just a loose correlation. The singleton rate fundamentally governs the error rate for arbitrary facts. After nailing down the problem of rare facts, the paper introduces the second major cause of errors, using a poor model. This happens when the model's architecture just isn't complex enough for the problem it's trying to solve. Think of it like trying to separate a circular pattern of data using only a straight line. No matter how you place the line, you're going to make mistakes. It's a fundamental mismatch between the tool and the task. So how do we connect this abstract idea of a poor model to concrete, provable failures? First, the authors formalize the link between a model's inherent limitations and its final error rate. They present Theorem 3, a neat little formula specifically for multiple-choice questions. It says that a model's error rate is guaranteed to be at least twice its best-case classification error, scaled by a factor related to the number of choices. In short, if the model is fundamentally bad at a task, it's going to generate a lot of wrong answers. To make this super clear, they use a great example, the old-school trigram model. These models only look at the last two words to predict the next one. They set up a simple task where two sentences are identical until the very end, where one ends with her mind and the other with his mind. A trigram model, with its tiny context window, can't tell the difference. It has to guess. Using their new theorem, they prove, in Corollary 2, that any trigram model will have at least a 50% error rate on this task. It's a perfect, self-contained demonstration of a poor model error. The model's architecture is simply not powerful enough for the job. Finally, they circle back to the letter counting example from the introduction. They suggest that the original model that failed was a poor model for that specific reasoning task, while a newer, more specialized reasoning model handles it just fine. This highlights that poor model is relative to the task at hand. Now we wrap up the discussion on pre-training errors by listing a few more culprits. First is computational hardness. Some problems are just fundamentally hard to solve, and no amount of data or clever algorithms can change that. AI isn't magic. It's still bound by the laws of computations. Second is distribution shift. This is a classic machine learning problem where the test data looks different from the training data. If a model has never seen a trick question like, what's heavier, a pound of feathers or a pound of lead, it might get confused and give a nonsensical answer. Third, and most famously, is go, garbage in, garbage out. The internet is full of misinformation and factual errors. If the model is trained on this garbage, it will learn to reproduce it. This is a simple but crucial factor. With the causes of pre-training errors laid out, the paper pivots to the second half of its argument, post-training. This is where we take the raw, pre-trained model and try to fine-tune it to be more helpful and less prone to hallucination. But the authors immediately throw up a caution flag. They argue that reducing hallucinations is an uphill battle because our entire evaluation system, the benchmarks and leaderboards that drive the field, actively reinforces the very behavior we're trying to eliminate. They call this a socio-technical problem. It's not just about better algorithms, it's about changing the culture and the rules of the game. This brings us to the solution. The paper starts by mathematically proving what we've all intuitively understood. With standard 0 or 1 scoring, guessing is always the best strategy. And I don't know gets you a guaranteed 0, while any guess, no matter how wild, has a non-zero chance of being right. So, a model optimized for score chasing will never choose to abstain. The authors then point out that we've already solved this problem in the real world. High-stakes human exams like the SAT or engineering entrance exams have long used penalties for incorrect answers to discourage random guessing. Test takers know the rules and adjust their strategy accordingly. So, they propose we do the exact same thing for language models. Their big idea is to introduce explicit confidence targets right in the prompt. Here's how it works. You tell the model, only answer if you are more than, say, 90% confident. If you're right, you get 1 point. If you say, I don't know, you get 0. But if you're wrong, you get a big penalty. This simple change completely flips the incentive structure. Suddenly, bluffing is a terrible idea. The model is forced to honestly assess its own uncertainty before speaking. By adjusting the confidence threshold and the penalty, we can tune how cautious we want the model to be. It's a direct, practical way to make models more trustworthy by changing the rules of the exam. And here's the hard evidence. Check out Table 2. It's a survey of the big, important benchmarks that everyone in the ASI field uses to measure how good their models are. The results are striking but simple. Almost all of them use a binary right or wrong grading system. And in almost every case, a model gets 0 credit for saying, I don't know. This table is the smoking gun. It proves the authors' point that the entire evaluation ecosystem is set up to reward guessing. A model that honestly admits uncertainty will get a lower score on these leaderboards than a model that confidently bluffs. With this evidence in hand, the authors make 2 key suggestions. First, they argue that the confidence thresholds and penalties shouldn't be some hidden, implicit rule. They should be stated explicitly in the prompt for every question. This makes the evaluation objective and fair. A single, well-calibrated model can then perform well across any threshold because it knows the rules of the game for each question. Second, and this is their big strategic move, they argue we shouldn't just create new, separate hallucination benchmarks. Instead, we should incorporate these new scoring rules directly into the existing, popular benchmarks that everyone already uses. This is a much more powerful way to shift the entire field's focus. By changing the rules of the main event, you force everyone to build more honest, trustworthy models to stay competitive. This final section is all about intellectual honesty. The authors step back and discuss the limitations of their own framework, which is always a good sign in a research paper. They start by acknowledging that their whole analysis focuses on plausible falsehoods and mostly ignores pure gibberish. This is a fair simplification, as modern models are pretty good at sounding coherent, even when they're wrong. Next, they address a big question. What about popular techniques like retrieval augmented generation, or RAG? RAG systems try to reduce hallucinations by looking up facts in a database before answering. The authors make a crucial point. RAG is not a cure-all. It helps, but it doesn't solve the core incentive problem. If the search fails or finds nothing, the model is back to square one. And if the evaluation system still rewards guessing, the model will guess. RAG is a helpful tool, but it doesn't change the rules of the exams. They also admit their proposed correct, incorrect, or I don't know system is still a simplification. The real world is full of nuance, with different degrees of wrongness and uncertainty. They call their own system a false, three-part system. But here's the key takeaway. It's a massive improvement over the current false, two-part system of just right or wrong. It's a practical, objective step in the right direction, even if it's not the final destination. It's a classic case of not letting the perfect be the enemy of the good. And so we reach the conclusion, where the authors tie everything together with a powerful final statement. They recap their entire journey. They've demystified hallucinations, showing they aren't some spooky emergent property, but a natural result of training. They begin as simple classification errors during pre-training, and persist because our evaluation systems are fundamentally flawed. The authors argue against creating more and more specialized tests to catch specific bad behaviors. The real problem, they say, is systemic. The major, mainstream benchmarks that everyone uses to compete are the ones that reward the test-taker behavior of confident guessing. Their final call to action is not to build a new test, but to fix the ones we already have. By making simple changes to the scoring rules, rewarding honest expressions of uncertainty and penalizing bluffing, we can realign the incentives for the entire field. This, they hope, will remove the barriers that currently discourage the development of more cautious, nuanced, and ultimately more trustworthy AI systems. It's a simple idea with the potential for a massive impact. Thanks for joining us today. Happy exploring together.